are, a couple thousand. But. So yes, the Galois theory. Oh, thanks. Let me try to make some progress today again in explaining what's the situation. So I'm gonna just try to go through Conrad's the Galois correspondence and just write down some results and see where we can get to here. Okay. So my apology if there's overlap, but I think that helps us to learn as well, right? So I'll be using Conrad's notation. Is like L over K, a field extension. So he uses K for the base field and L for the extension field, right? And then the basic definitions that I was fussing with is the F, or well, here's the F fixing automorphisms of L. So maybe F is a K intermediate field, I guess. I don't know. Anyway, L over F is equal to what? Sigma an automorphism of L such that what? Sigma of alpha equals alpha for all alpha in F. So this is the F fixing automorphisms, and then we can talk about the fixed field of H, right? This is alpha in L such that sigma of alpha equals to alpha for all sigma in H. And here, this is where H is a subgroup of the automorphisms of L which fix K. All right. So the fixed field and the F fixing automorphisms like that. And then, let's see here. He says the correspondences F so we have F, he uses this notation corresponding to L over F and H corresponding to LH. So these are the Galois correspondence between fields and automorphism groups and vice versa, right? Subgroups. So like well, anyway, let me write the table here, the picture here. And so we have L, and then F prime, F, and then K down here. And over here we'd have like id ought L over F prime. L over F ought L over K. Let's see here. So this is a tower of fields, and this is a subgroup diagram written from largest to smallest. Right, so the the size, if you will, of these two pictures is sort of inversely related, right? Biggest to biggest to smallest versus smallest to biggest, so to speak. And the inclusion reversing we talked about before, but I'll write it up here. So it was just this, right? If f is a subset of f prime, then ought L over f prime is a subset of ought L over f. So inclusion reversing. Another thing that, so yeah, like, by the way, consequence of these ideas that we've talked about before, but it's good to write again, is that you can see that f is going to be a subfield of the fixed field of the automorphism group of L over f. And you can also see that H is going to be a subset of the fixed field fixing automorphisms of so this. I don't know how to say it in words. So if you look at all of the automorphisms which fix the fixed field of H, well, then H is in there. So, yeah. He says this is practically a tautology. You may need to read through that 2 times to see it. Anyway, all right. Now, this is a definition I don't think I've stated before, but I'm actually very interested in this definition, and I want to like incorporate it into our conversations in as much as we can. Definition: the roots of a common irreducible polynomial in Kx are called K conjugates. I was looking to say this the first day we were talking about things, but I don't think I quite got to it, did I? If I did, and I already said this, and I forgot that I said it, my apologies, but I feel like I missed saying this day one, and I meant to. Right, so, for example, right, if we have, x squared plus 1 is an element of R of x, right? Then, as you know, x squared plus 1 is x minus I times x plus I. So what are the roots here? I minus I. Right, so alpha equal to plus or minus I are, according to this language, are conjugates. So he apologizes for the language. He's like, I'm sorry, it's too, it's so unfortunate that we call them complex conjugates, right? But, all right. Another example, if you had x squared minus 2 over, say, q, then alpha equals to plus or minus square root of 2 are q conjugates. All right, those are q conjugates. And the big theorem that we proved was that if we have, and this is his theorem 2.4, which I think doesn't hurt to say again, if sigma is an element of ought L over K, and f of x is an element of the polynomial of over K, then sigma of f of alpha is equal to f of sigma of alpha for all alpha in L. Thus, sigma permutes the K conjugates of f of x. In other words, the K automorphism of L permutes the roots of f of x in L. So where are the K conjugates of f of x? In L, right? They're in L. Anyway, and the corollary 2.5 is even more clear. It's just like the group L over K permutes the K conjugates in L. Maybe I should just write that. That's even clearer, easier to remember. Corollary 2.5. The group ought L over K permutes the K conjugates in L. All right. And then his next section, he has an array of results, like theorem 3.1. For any finite extension L over K, the group L over K is finite. All right. And then he has theorem 3.4, which connects an isomorphism. Well, maybe I should just write it out. Yeah, let me write this. Theorem 3.4 is kind of heavy. So theorem 3.1 for finite extension L over K, the group ought L by K is finite. All right. So that's nice. I mean, if we're looking at a finite extension, we want to understand what's the group of automorphisms of L which fix K. We're dealing with a problem of finite groups, right? Which means that there's like a finite number of possibilities, and we can check them by just brute force calculation if it comes to it. Horrible, but true. And that's more or less what we've done in examples that we've already done in here, isn't it? Think about back to the examples we looked at, that's what we've done. Now here's the theorem which is deeper. Sigma, a mapping isomorphism from K to K prime, isomorphism of fields. All right, and let f of x be a polynomial over K. With splitting field L, and let likewise sigma f of x, the corresponding polynomial in k prime of x, all right, with splitting field L prime, all right, then the degree of L over K is equal to the degree of L prime over K prime. And sigma extends to an isomorphism of L to L prime. All right. So we're given like K sigma, right? K prime, saying that, and we're also given that there's, this is the splitting field, that's the splitting field, right? So part of what the theorem's saying is that you can extend sigma up to here in sort of the, we could call it sigma tilde or something you want, but the isomorphism naturally extends to the splitting field. So sigma extends to, let's say sigma extends, instead of using sigma, let's use tau up here, okay? So sigma extends to tau. What does it mean that it extends? That means if we look at tau restricted to k, it's just sigma basically, ignoring the okay, technically speaking, the codomain of tau is L prime, whereas the codomain of the restriction of tau to k is technically k prime. So with the understanding of the codomain mismatch, I don't have a good notation for it. Anyway, but it's more than that. And there is, at most, how many such choices, how many such tau are there? There exist at most degree of L over K such tau. So there's only, that many extensions. Then this is the proof he gives on pages 5 and 6. It's 2 pages. And then, so let's see here. Let me look at his example right quick. So example 3.5, we have Q adjoins square root of 2, square root of 3, so the biquadratic extension over Q. This has degree 4, and so in theorem 3.4, if we use k equals to, he's like put k equals to k prime equals to Q, and L equal to L prime equal to Q adjoin square root of 2, square root of 3, right? Well, first of all, is that legitimate? Like, what is L and L prime the splitting field of? But when we say splitting field, we have to be talking about a polynomial. Splitting field of what polynomial?
Over Q would be x to the fourth, x to the fourth minus 2 plus 5, something like that.
Yeah, it splits x squared minus 2 times, oh, you multiplied out? Cool. X squared minus 3, right? That's the polynomial that splits. And then, of course, we're talking about the identity. Sigma would just be the identity map in this case. But that's the theorem says it can be extended. Let's see, it's degree 4, right? So this says that the identity map on the rationals can be extended in at most 4 ways because this has degree 4 over Q, right? And in fact, that actually happens here, right? Because the the tau, well, it's unfortunate the letter I've chose, right? But the tau on mapping from L to L, what were those 4 automorphisms? Remember there?
Oh yeah, 1 sigma tau tau sigma.
Right. So now I'm using the tau notation as a arbitrary one now. I used it as a specific thing in our previous example. My bad.
Yeah, no, we can just say that.
Here, I know how to fix it.
Alpha beta.
Check it out. I'll fix it. Oh. So you're like
1.
tau equals to alpha, tau equals to beta, or tau equals to alpha beta, where alpha fixes the square root of 2, but switches root 3 to minus root 3, where beta fixes the square root of 3, but sends root 2 to minus root 2, and then where tau sends both root 2 and root 3 to minus themselves, right? So, and we had the explicit form. Oh yes, technically, but they're equal, so, yeah. But in fact, in this case, there are 4. In fact, there are, not only there at most, there actually are 4 in this case, right? Now, so yeah. And then, let's see here, what else? So, corollary 3.6 was that the number of automorphisms of L over K, right, is less than or equal to the degree of L over K, right, for L is splitting field over K. But then what did we say? If f of x is separable, then there are L over K extensions, right? So basically, we can cross out this at most, we can cross out and say, we can just basically cross this out if f of x separable. That's the theory, right? If f of x is separable, there are, in fact, that many extensions of the isomorphism, distinct ones. All right. So let's see here. Goodness. I think I can erase this. I'm going to erase this theorem now. And replace it with a laundry list of nice sort of, this is pretty much equivalent ways of, well, I don't know if it's an are these equivalent? These are, it's an if then. If L over K is finite extension, right, and the number of K-fixing automorphisms of L is equal to the degree of L over K, then number 1, the automorphism of K-fixing automorphisms of L, the fixed field of that is just K. 2, L over K is separable. That meaning this means, because I don't think we actually defined, well, I guess we did, but I've forgotten it, This means every number in L has a separable minimal polynomial. Every alpha in L has m alpha k of x in k of x separable. And 3, for alpha in L, all right, its k conjugates are simply sigma alpha, as sigma runs over, or you could say runs through, if you like, ought L over k. For every irreducible polynomial in kx with a root in L splits in Lx. In other words, this is familiar from basic algebra as the statement, if you have 1 0 for the polynomial, right, you get all the others, you know.
Wait, huh? You get 1, 0 in all the polynomials.
If you have one root for irreducible polynomial in L, then you get all of them. Provided this condition up here,
Okay.
that the number of, you know, k-fixing automorphisms of L is L
Okay, so let's say,
with that condition, yeah. It is, of course, not the case if you have a finite extension which doesn't meet that. Like, what's an example, what's our standard, like, go-to example of something which doesn't meet the criteria of theorem 3.13 would be, you know, Q adjoin the cube root of 2 over Q, right? Because we saw that if this is L and this is K, then ought L over K is just equal to the identity. And of course, you know, f of x, x cubed minus 2 has just one of its zeros, one of its roots in L, right? But indeed, while this is a finite extension, it's got degree 3, you know, it does not meet the criteria. The number of automorphisms, of k-fixing automorphisms L is not 3, it's 1. And so we don't get this list of goodies for this example. Yeah. In contrast, this one we do, because there are 4 automorphisms, and this is a degree 4 extension, this biquadratic extension. And then 5, L is the splitting field over K of a separable polynomial. Which is an interesting thing in the context of theorem 3.13, because if you take a look at it, there is no polynomial in this theorem.
no.
So it's saying that there exists such a polynomial in this case. So And you'll forgive my laziness, I'm going to again skip the proof. It's a page. All right, so condition 4 is called this condition right here. If every irreducible polynomial in K with a root in L necessarily splits in L of X, this means that L is normal extension of K, right? It's a normal extension. In example 3.15, he says any quadratic extension, separable or not, even in characteristic 2, is normal. And then he proves it. I guess I can afford to do that. Actually, I'm going to behave and not do that. Oh, fine. Example 3.15. As you know, I wrestle with indecision. Any quadratic extension separable or not. All right, so if we have the degree of L over K is equal to 2, okay, that's a quadratic extension, right? Then he says any element of L has a minimal polynomial in K of X of degree 1 or 2. Why can't it have degree 3?
Wait, so okay. If L over K is degree 2, then alpha of L is, the minimal polynomial of alpha, because it splits.
No, I mean, why can the degree of, so like, remember this? If we take K and we extend by alpha, right? Yeah. The degree of that over K is what? It's the degree of the minimal polynomial of alpha over K of X, right? But we also know that we have the following picture: L, K alpha, K.
Yeah, and L over K is 2, so that gives you...
Right. That's precisely. So that's why we know. It's more basic even than that. Well, yeah. And this is at most 2, right? So this has to be a divisor of 2. Mm-hmm. So it's either 1 or 2. If it's 1, if this is degree 1, then that's 2, right?
It's isomorphic to L,
right. So if it's
it's either isomorphic to the whole thing or it's 1.
Precisely. So then, what are we trying to show? I'm trying to explain why. All right, so that we're trying to claim, our claim is that any quadratic extension is normal. Okay? So we're supposed to do what? Every irreducible polynomial in K of X with a root in L necessarily splits in L. Right? So, of course, if you pick alpha in L and it has degree 1, it's already split. That's stupid. So let's suppose that we're dealing with degree 2, right? So you've got m, I'll just say m of x, equal to x squared plus bx plus c, right? So that, and we're assuming that that has a root, right? Because we're looking at irreducible polynomial in K of X with a root in L, right? So let's call the root R. So that's r squared plus br plus c, and that gives us 0, right? So how can you factor?
Definitely got an x minus r.
All right. Oh, yeah, very good. So the factor theorem gives us that much.
So we definitely have an x minus something.
Yeah, put an x there.
Yeah. Okay, so this is a homework problem.
How about this?
X squared, yeah. So b minus r.
Yeah, so we better do plus b So let's see, here we get run out of space.
You gotta get rid of your r's.
Okay, so hopefully that works. We better get remainder 0. I've run out of chalkboard, so all we can do is check this now, okay?
Yeah, x squared dx rx minus rx minus rb minus r squared, or I guess just r squared.
Minus r squared minus rb, right?
Yeah.
But,
Okay, so you got bx
see what that is, though.
r squared. Oh, but you keep your x squared.
Uh-huh. Yeah, that's fine. X squared plus bx, this,
Oh, yeah.
see.
Yeah, I got you. Oh.
So, split. Yeah, I mean, this was definitely this is the problem. It's actually kind of funny, right? I think the homework problem seemed harder because it was more specific. Like, this is abstract, and yet it became, it's almost easier in the abstract than it is if you make it over, like, k equal to z3 or something. They're just, so he says it's normal. A normal extension is one where every irreducible polynomial in k over k that has a root in L necessarily splits in L. That makes L a normal extension. All right. And then he says, for any finite extension, the following are equivalent. L over k is normal. L is the splitting field over k of a polynomial in k of x. So for finite extensions, normal is equivalent to splitting, the splitting field. All right. And of course, this is a special case of that. And then, so that finally brings us back to Galois extensions once more, right? What was our definition? Okay, so here's theorem 4.1 is kind of an improvement on this, a slight tweaking of it. Let me write it down. Sorry, it does take me a while to get all of the theorems in this material kind of up and processed, you know? It does take some time. It would take even more time if I actually proved all of them. Sorry, I'm not doing that. But here it is. For a finite extension, L over k, the following are equivalent. And taffy. 1, the number of k fixing automorphisms of L is equal to the degree of the extension of L over k. 2, the fixed field of the automorphisms of the k fixing automorphisms of L is just k again. 3, L over k is separable and normal. Remember, that means that separable means that every element has a separable minimal polynomial. And normal we just talked about. 4, L is the splitting field over k. Of a separable polynomial. In kx. There's a corollary 4.2. I think we can prove the corollary. Let's try to do that. Corollary 4.2. If L over k is any finite extension, then the number of k-fixing automorphisms of L I wrote it the other way around. L over k, k-fixing automorphisms of L, divides the degree of L over k. You're fine. Proof? He's like, okay, since L over k is finite, we know that the automorphisms of L over k is finite group. All right, that was by theorem 3.1. He says, let f equal to L ought L over k. So in other words, let f be the fixed field of the k fixing automorphisms of L. All right. He says, then ought L over k equals ought L over f. Is that obvious?
Oh man, I'm sorry. I thought it said ought L over k is equal to ought L over k, and I was like, yes. I thought you were
Yeah, right.
well, f is L ought L over k. Is a fixing. Well, or k and L ought k. Let me make sure I go back to the LH definition. L of h is such that alpha and L.
Yeah. See, if I have a doubt, I'm going to have to pick an element in one and see that it's in the other, right? Mm-hmm. So, which way do you want to go? I mean, if they're equal, it should be doubly contained, right?
Yeah. So pick a thing in F and see if it's in K.
All right. So I'll pick sigma in ought L over k. that means what? That means that sigma of alpha is equal to alpha for all alpha in K, right? And sigma is an automorphism from L to L.
Well, we know sigma takes alpha to alpha. Okay. So we have to show that's an F. I mean, we have to show it's in K.
Well, we need to show that the question is it in here?
Is it in there?
I mean, I'm trying to show this is a subset of that. So I need to show that sigma satisfies the criteria for being in here, which is what? Sigma is an isomorphism from L to L.
Yeah, that's
Got that.
Yeah.
It has to fix F, right? So why is it that sigma of, let's say, little f is equal to little f for all f and f, right? Why is this?
Because
What does it mean for f to be an f?
wait. Well, we know that L.
I mean, tell me, so the real question here, Audric, is what does it mean for little f to be in big F, right? What does this mean? Unwrap that. F is where it's in this fixed field of the automorphisms of, right? Which means what? That means that sigma of F is equal to F for what? For all sigma in aught.
LK. Okay, but we have a consequence.
Oh, but sigma is in aught L over K.
Yeah.
So for any so yes, for all f, we have this condition because sigma is exactly the thing that fixes f. In other words,
No, it's just like this looks like a tower problem. Like you can solve it with the tower thing, because one of these has to like L of aught L over K. We know like
oh, so you're like L is up. Well,
yeah, I'm trying to get the
L
right,
is over F is over K, I suppose.
Yeah. And then so we have aught LK on the bottom. And then aught LF. And then the identity. And then so we know sigma's an aught LK and we have reverse containment of aught LF.
Uh-huh.
So therefore sigma has to be an aught LF.
Oh, but okay, so I guess what you're saying is that I have just established the uninteresting direction.
I think so.
Yeah, okay. Thanks a lot. So you just got from your tower what I got from what's written in red and green here,
Yeah.
which is that this is a subset that way.
Yeah. Now we have to show the other way.
The other way, right?
That
So let me-
aught LK is a subset of aught LF.
Yeah, so let's pick,
It looked familiar. That's why I
Sure.
went to that.
so let's let sigma be an element of aught L over F, right? Then, so that means that sigma of alpha is equal to alpha for all alpha and F, right? Where F is equal to this right here, which means what?
Sigma's an aught L over F, and that means. Oh, okay. I mean, that's the definition. So we need what?
What is F? the fixed field of the automorphisms of L, which fix K, yeah.
Yes. But we just said sigma's in, and that. We just said sigma's in the is in the fixed field of F and L.
Yeah.
Did I say that right? And so that implies that sigma takes alpha to alpha for every alpha in F, which is equal to
So this, in other words, we could also say that sigma of F is equal to F for all F in F. I'm just changing the letters. Sorry, I'm an idiot.
RF is L ought
My bad.
K. Which is ought LK
Yeah.
contained in L over.
I'm trying to show it's in L over K at the moment, right?
Well, there's a consequence here that says
What do I need to check?
here
I mean, to show that sigma is in here, what do I need? What do I need to test? I need to test, is sigma of K, let's say, equal to K for all K and K, right? I mean, certainly it's an isomorphism from L to L, that's already given.
I think
Do I get what's in red from what's in yellow?
you do, because if we go back to the definition, it's a consequence that ought of L over K is contained in the automorphism of L over F. If I'm reading this right. Because we've already said containment in one way. Hence, ought of L over K is contained in ought of L over F. Unless I just said, I think we've already proved this, never mind. Yeah, we already showed this.
Oh, okay.
Sorry.
It's okay. All right, so let's think about this for a second here.
Okay.
So I need to show this, all right? I have what's in yellow right above.
Yeah.
So alpha in, now F, this is of course a subset of,
Well, that right there is for every alpha in L, sigma sends alpha to alpha for every sigma in ought L of K. Yeah. So we need an alpha in, so we need to make, so that's a K, which is what we're considering, what we're trying to say is alpha. So essentially, if we can just show that sigma of K sends K goes to K, we're done. But we have that for every sigma in H, we have,
the question is, does K, does K and, is K and K, does that, is this a subset of F?
is K a subset of F? No, not by, oh yeah, K is a subset of F. Set it up there at least.
So then we know that So we have it then, because if this is true for all alpha and f, then if every alpha and f is also in K, then I think we're done.
So is this just a proof by definition, essentially?
This part of it, we're not done with it. That's just,
Yeah.
I just stopped here to,
Oh yeah, because we still got to say it divides.
yeah, I just wanted to waste your time on that one.
No, because like, yeah, I just got stuck on the tower thing because I was like, I feel like this should be.
No, I think your tower argument's fine. Let's see here. And it's that time of the week that I start making stupid mistakes. So let's forge ahead here. So he's like, thus f so f is equal to L of, I thought he said the same thing again, but he has changed the letters, L over f. So therefore, by theorem 3.4.1, the number out of automorphisms of L over f is equal to the degree of L over f.
Which does divide. Wait, never mind. Wait. We're trying to prove ought L divided by L over K.
So we have satisfied criteria 2 of theorem 4.1.
Yeah.
So then we get that, hence 1 holds, right? We get the number of automorphisms. Oh, it's right here. Sorry, dummy. I've already written it. Duh. Okay, then what?
So if 1 holds, that means 2 holds.
Yeah, this is 2.
That's 1.
And this is 1.
Okay.
Using the following as equivalent. Yeah.
And we need to show that it divides.
The number of automorphisms of K. So then the thing is,
Wait, but we know. Oh, never mind. Wait, yeah, we know that the number of ought L over F is equal to ought L over K. So you can interchange that, can't you?
well,
No, I don't think that helps us though, because you still need to divide L over K. Or L, the degree divides it. It divides the degree. But no. But we know that we do know that L over K, the degree of L over K is equal to the degree of L over F.
oh, look at this.
And F over K.
Yeah, I mean, but notice we already have these are equal, right? So the number of L over K is equal to
Degree of L over F.
degree of L over F, yeah.
And degree of L over F is the degree of, and multiply that by.
So the degree of L over F
You can multiply
is,
by.
it divides the
Yeah.
degree of L over K, right?
Yeah.
From the tower.
Yep. Okay, my line of thinking was right.
Yeah, then that gives us that. All right, so sorry.
No. I thought it was helpful.
All right. Okay, finally, definition of Galois again. Finally got back to the definition of Galois again. Fine, towards the end of, almost the end of today, we got back to the definition of Galois again. That's good. So definition